Okay. So yeah. So what we are doing here, the geometrical intuition behind the PCA is that whenever we have, if the basic example was we were trying to convert 2D to 1D, and while converting from 2D to 1D, what we did, we have just removed those features where the spreadness or the variance was very less. So what we are conserving the we are conserving those features, okay, or those directions where the spreadness is high, or you can say the variance is high. Is it clear till now? Like we are removing those things where the variance is less or variance is very less, and we are just conserving those direction or those features where the variance or the spreadness is very high, right?
Yeah, understood.
Okay. Yeah. So this is the basic geometrical addition. Now we'll see how generally we do. So this was the basic. This was a very simple data set we were taking. Okay. So this is a very simple data set. For that we did. Now we'll see a bit complex data set, and that also in a two dimension, and that we need to convert that to a one dimension. Okay. So this is a simple. What we would like to reduce the dimension from 2D to 1D. We just skipped the one. Why we skipped? Because the spreadness was very less, or the variance was very less in this F1 direction, or the F1 feature. By reducing F1, we are losing less information. Why we are using less information? Because that data set, the features one was having almost a constant value every time. So that's why that value is not helping the model to build a good model. Okay. Now we are preserving the direction with the maximum spread. Okay, preserving the direction of the maximum spread means we are just, like for example, in the earlier example, we just preserve F2. F2 was the direction, or F2 was the feature where the variance was maximum. Okay.
Sir, I
Now
have a
let's,
question.
yeah.
Let's take the simple variance calculation. In this example, we are considering two variables, F1 and F2. Let's say I calculate the variance. So
Hmm.
if the spread is less, usually the variance for F1 metric will be very low. So let's
Yeah.
consider this as one scenario. And the
Huh.
other scenario, let's apply the PCA on both F1 and F2. And what you are saying, even PCA try to remove those variables which are having less spread. Does
Yeah.
both the scenarios yield same result or a different result, sir?
Okay. The first question. What was the first thing? I just
First thing,
skipped
like
that.
I'll simply calculate the variance metric for F1 and F2. So which will give me the, what is the spread of these two variables, right? The variance x minus x mean by
Yeah, correct. So variance, normally you have calculated the variance for
simple variance,
F1,
exactly. The summary
and
spread.
variance you calculate the for F2.
Yeah,
Okay.
F2.
Yeah.
So if the spread is less for F1, then I expect my variance to be very low, right?
Very less. Yeah, it should be very less.
As opposed to this, how this is different in the PCA, sir? Like, you are saying like, PCA is also trying to identify the variable which is having the less spread, right?
Huh.
So how these two are different? I mean, are these interchangeable? No, right?
F1 and F2.
No. I mean to say the way how we are calculating this, thing between but I mean, why can't we use a simple variance metric here instead of PCA? That's what I'm trying to ask. Maybe my question can be very basic question here, so just trying to clarify that.
Yeah. So I'll just clarify your doubt. Okay. I'll just go. I'll discuss this one, and maybe that will clarify your doubt.
Sure,
Okay.
sir. Sure.
Hmm. So see the if you see the math behind the piece, like we are doing the only these steps only. What we are doing, so I'll just tell you. So we are taking the variance matrix itself. Okay. So what we are doing here, we are not doing. It's not like a very difficult algorithm. It's a way one of the very basic algorithm. Okay. Only the name is like seems like it's a very like difficult algorithm. It's a very basic algorithm PCA. So the math behind this is we are just able to get the we are just finding one direction. We are just our optimization problem, right? Our objective, what is our objective here? So in the PCA, our objective is to get that direction. Like if I want to get, like for example, I'm trying to convert from 2D to 1D. Okay. So trying to convert 2D to 1D means what? I just want one dimension. One dimension means what? One feature direction, right? So I need only one direction out of these two where the variance is very high. Okay. This is what I am trying to say from the starting, right? Is it clear? Hello.
Yes, sir. You are.
Yeah.
Yes.
So I'm just trying to get one direction where the feature or where the variance is very high. This is what I am trying to do. So, and this is our objective itself. From the starting in the PCA itself, our objective is to get one direction. If I'm converting this to from some larger dimension to one dimension, then I need one direction is only where the variance is maximum. Okay. So our optimization problem, or you can say the objective of this PCA itself, is only to find one direction where the variance is maximum. Okay. And that direction I need to find. How will I find that? That we'll be seeing later. Okay, there are so many techniques of problems like gradient descent or some techniques are there, and we are like from the starting, we are in this algorithm itself, we are just finding one direction where the variance is maximum. That's it. And that direction, how will we find? There are many techniques to find like variance. Either you are maximizing the variance or you minimize the error, reconstruction error. Okay, so we are doing the same, like whatever you have understood like correctly. So we are just doing the basic thing only. We are just finding a direction where the variance is maximum. That's it in the PCA, and nothing else we are doing here. Okay, but the point is, you'll not find the data set much like easier. Like here, we got a very simple data set, right? So here the data set, like, when we'll just plot the scatter plot and we can directly say, okay, but we'll not get the data set like this. Like we'll be having a data set like in n dimension. N can be like 500, 800, like 1 lakhs. Okay, okay. So here I'll just, so that was a very basic example. That was a very basic data set. Here we'll get some a bit complex, not much complex, but a bit like more complex than the earlier example. So here I'm having a data set. These are all data set. Okay, so this is the data set. I'm having of two features like F1 and F2. Okay, so F1 and F2. Here also I'm having the two features. Okay, so what I told you, what I need those direction only where the spread is maximum, right? Here also I'm having two features F1 and F2. I need to convert this 2D to 1D. Okay. So can somebody tell me which direction, what should I do here if I'm having this type of data set? All this cross marks is the data set. So what should I do here? And you already know the objective. What I have to do, I need to get one direction where the variance is maximum. Okay. I need to remove all the direction where the variance is minimum. Okay. So what I will do here? Can somebody tell me?
Do we change the axis and then take the variance
Okay, so I need to change the axis. Okay, so that's the
in the
correct point.
direction in the
Okay,
direction of the maximum variance?
okay. In which direction from the data set? In which
Orthogonal
direction
to
should I?
the, sorry,
In which direction? I just told F1. I need to shift. I need to rotate. In which direction?
that will
This.
be
Okay, so see. So this is the data set. If I'll just take the so how generally you calculate the variance? Like, or the variance is simple by the even from this scatter plot. You will tell, okay, in this F1 the spread of the data set is from here to here, right? And in the F2 also the spread is like from here to here, right? So now you will tell, okay, earlier you were saying if you are having two features, and if you are having two features in the earlier example, you can directly say, you have directly told, okay, so this feature, the spread was very less, so I have just excluded this feature. Here the spread is like almost same for both the axes, right? How will you convert from 2D to 1D? So one of the person told, I need to rotate. How will I rotate, and where should I rotate this direction? Where should I fix this F1 now? Can somebody tell me?
At an angle, like slope is equal to m tan theta, na? So at that angle theta we need to rotate.
Oh, okay. So which direction? F1 dash. I just told. I just shown F1 dash, F2 dash. In which like this or like that. How
F1
will I
dash, na?
F1 dash? Correct. So in F1 dash, why we are doing in F1 dash? Because you can see this. Whenever I'll take the projection of all the data on this F1 dash, I just rotated this F1 to F1 dash. Okay. So I need the direction. From the starting, I'm telling you what is my objective. I need the direction where the variance should be maximum. That's it. So that's my only objective I need. Okay, there are some constants, there are some like conditions also that I'll tell you later. But the first basic objective is to get the direction where the variance is maximum. That's it. So for us now, I need this direction, right? Why I need this direction? If you'll plot, if you see the projection of all this data on this direction only, I'm just concerned about the direction. I don't need the magnitude of this direction, and I don't need anything. I just need this direction. That direction means I need a unit vector in this direction. If I'll just plot, take the projection of all these data sets, you'll see the variance is from here to here, or the spreadness, you can say, in the basic English word. And the spreadness of this in the F2 dash will be from here to here, right? So now I've just rotated all the axes F1 and F2 with some theta, okay, here. Now I'm having F1 dash like this and F2 dash like this. I've just took the projection of all the data set on this unit vector and this unit vector. Okay, both are orthogonal to each other. So I've seen that in F1 direction, F1 dash, the variance is like very large, right? So the variance is very large. But in F2 dash direction, the variance is very less. So what I can do here, so I can just keep F1 dash and I can remove F2 dash, right? So by keeping F1 dash, I'm able to preserve much of the information, right? From the figure itself, you can see the variance is very large as compared to F1, F2 dash, right? So F2 dash can be removed. So this becomes the same case as of the blackness of the hair. So this feature F2 dash becomes the blackness of the hair, and F1 dash becomes the height of the person, and I need to predict something. Okay, so here also I need is this direction. I need this direction. F1 dash I'll keep, F2 dash I'll just remove that. So here also I just converted from 2D to 1D, right? So this is what PCA does. So if you are having any doubt till now, you can ask me.
It's clear, sir.
Yeah, it's clear, right?
Sir,
Yeah.
so let's say F1 is like the blackness of hair and F2 is the height or something. So what would be F2 dash or F1 dash? Like what features would those be?
Okay. So what here? So you can't like see what it generally does. It has rotated the axis, right? So F1 I was having earlier some features F1, and F2 I was having earlier, right? Some F1 and F2 features. But what it did, it just needs some direction where the variance should be maximum. Okay, so randomly it just started taking. So you can't say what is that exact feature. Okay, so it is some sort of mixture, and then it came with some direction. Okay, it's not like exact. You can't say exact what is that feature. Okay, because it will start working, and it will start working, and it will start taking some random directions, and in the end you will see, okay, because you already gave the algorithm, you need that direction where the variance should be maximum. Okay, so it will start rotating from some theta, like theta tends to some smaller value, and in the end, if at F1 dash it will tell you, okay, this is the direction that you need, because you gave me the work, to find one direction where the variance should be maximum, and there are some constant also. Okay, so that is like that we'll discuss later. But till now you have just gave me one work, and I did your work. I just gave you one direction where the variance is maximum. You can't say what is that exact feature. It's some sort of mixture, and it came in that direction. So you can't directly say what is that exact feature that you got in the end. Okay, because it's some sort of mixture and all.
Okay, thank you, sir.
It's clear? Yeah.
May I ask the question?
Yeah.
Yeah, is this where we actually start using affine subspaces, because this rotation of space and everything was shown in affine subspaces?
Rotation of?
A rotation of a vector space, if we really want to actually do it, we were using affine subspaces. Is this going to be influenced by that, or do we use affine subspaces here when the rotation has to happen?
I'm not able to get your point.
I mean, like the application mathematics wise, is this
Okay.
where we use affine subspaces, or
No, that is the one aspect or the one use of that rotation, but there
okay,
can be like a large number of use
okay,
of those vector like subspace or the whatever, like that rotation part.
okay,
But this is the one use that generally PCA does. The one use of the rotation of the vector.
okay.
Okay. So yeah. Okay. So what here also we need just one direction where F1 dash is like spread of the that we have already discussed, and we are dropping F2 dash, and we are just keeping one dimension. So here also what we did, we just converted from 2D to 1D. We were having two dimensions, so we have converted to one dimension. Okay. So in the starting example, what I told, I just removed the first feature. Okay, so that was just excluding the feature. Here we are not excluding the feature. Okay, we are just from that two features, from the two dimension or the two features, we just got one dimension or one direction where the feature was maximum, and where one that was orthogonal to other, that was like with the some rotation or something we got. And we got two direction where the one direction the variance is maximum, one direction the variance is minimum, and we just kept the dimension one direction where the variance is maximum. That's it. So we just converted that into one dimension. Okay, so here we did uh, this part. Okay, because the data set was a bit complex, that's why we did like, but we'll get like this is also not that complex data. We'll be getting the data like that are like hell. Okay, so this was the basic things behind how generally we do from 2D to 1D. Okay, so what I wrote here. So to find the direction F1 does says that the variance of the project is max. Okay, so this is the math behind that. Okay, so I'll just start. What is the exact math behind that? So I was having this data set. Okay, so what I need this direction u1. Okay, I told you u1. I'm not caring about the magnitude of this vector. I'm just caring about the direction of the data set. So I need just some unit vector. Okay, I need some unit vector where the direction where the variance is maximum. Okay, so this is the unit vector or unit direction where the variance is maximum. Okay, so if I'm having scatter plot for this scatter plot for this data set where I'm having only two features, I can directly say this is the direction. But normally we don't know anything about the data set also. Like we have the data set, but you can't like if the data set is in 100 dimension, you can't like imagine how that like it will be shown on your two in your display. Or like here we were having only two features, so we can directly say. So from here, like from two dimension, like we now started to work on n dimension also. So however it was working for the two dimension, like we have converted from 2D to 1D, it will do for D to D dash also. So here we from the two dimension, we were if I need to get the one dimension, I was what I was doing, I was just getting one direction where the variance is maximum. If I need to get from D to D dash, I also need some D dash dimensions where the variance has maximum. Like I'll be having what? I'll be having one dimension. I'll be having like for example, I need to convert from 10 to 3D 10D to 3D. Okay, so I'll be needing three dimensions, three directions. I'll be needing three directions. Okay, so for one direction, the variance would be maximum, like at the peak. So the second would be the less than this, and the third would be the lesser than this variance. Okay, so I'll be needing from the like the largest, so three most largest like direction I'll be needing where where the variance would be like one for one, the first for the first will be maximum, for the second maximum, for the third maximum. Okay, so in this way I'll be needing from the 10 dimension, I'll be needing three dimensions if I need to convert that from the 10D to 3D. Okay, so okay, that's the part. So we'll start working on the maths part now. So what we are doing here, so I'll be just I'll be just taking the projection of all the data. So I was having this data set, so I'll be doing for the two dimension, and similarly we can do for the n dimensions also. Okay, so for this two dimension, I was having this data set and this F1 and F2, right? So I just like, for example, U1 was our, U1 is the direction where the variance is maximum. So I just like, the algorithm will start working for some random n number of times, and like n number of times, n can be infinity also. And in the end, it will give you the U1 direction, right? So it will start from some random theta also. So like for example, it came here like u1 this direction it came. So how will we calculate the variance? So to calculate the variance, I need to project all the data set on this direction, right? So I'll be projecting, like for example, I have this data set. I'll just start. Okay, I wrote here also. Hmm, 1 second. Okay. So yeah. So I was having, I'll do for the 2 dimensions, and similarly we can see for the n dimensions also. This was F2 and this is F1. So I have some features here, one data set, okay, and this is the U1 I got. This is the U1. So there are data set. I'm just representing one data set to for the calculation, like so that the calculation will be simpler. Okay. So now, okay. So this is the data set I'm having. This is X1 data set. Okay. So this is the U1. So if I need to project this on this X1 dash, this will become X1 dash. So this is our X1 dash. Similarly, this is Xi, and that there are like lot of data points here. Okay. So we'll be projecting all the data. We'll be projecting all the data points on this direction or this unit vector that I've got. Okay. So I'll be projecting all the data sets. So you'll be getting what? This will, so what will be the projected value if I need to project this vector on this U1? What will the projected? So the projection of what? Projection of Xi on UI. What will be the value?
UI xi by inner product
UI.
UI xi by inner product UI into U.
Yeah. So it will be like UI Xi, and then upon whichever vector we are taking the projection, the magnitude of that vector. Okay. And we already told you, like the magnitude, we are not caring about the magnitude. So this should be 1. Okay. So mostly the projection of what? The projection of Xi data points on UI is what? UI Xi transpose or UI Xi. Okay. UI dot Xi. UI means what? We have only one this UI. So UI Xi. Okay.
So we take a orthonormal vector for defining UI, is it?
Yeah. So that will be, yeah. So we generally take the, so that will get related to your eigenvectors, okay? Because we'll be having different number of eigenvalues. So all the eigenvalues are distinct. So all the so this is related to eigenvalues and eigenvector. So
Okay.
see, so I'll tell you the final result, and then I'll start. So this is what, so this vector, how will you get, so this vector, like for example, you have constructed, you are having this feature matrix, right? X transpose is what, so you have this feature matrix, X or X transpose, whatever you want to write. Okay. So you'll be having some covariance matrix you will get from X transpose X. X is your feature matrix. Okay. So for this X transpose X, if I'm having X transpose, like for example, you were having some n number of data set, n cross d you were having. So n data set you were having, and you were having d dimension. Okay. So if you write this X transpose A, it will come in what? D cross D dimension, right?
Yeah.
Okay. So you'll be having how many for this S covariance matrix? You'll be having D eigenvalues, right?
Yeah.
And this D eigenvalues will be having D orthogonal eigenvectors, like all will be like perpendicular to each other, whatever you'll be getting eigenvectors, right?
Yes, sir.
Okay. And this D eigenvalues, so this D eigenvalues, if these are distinct, so all this will be having some random, some magnitude, right? So like for example, one is lambda1, the second one is lambda2. I'm just writing in the form of decreasing order, and some will be having lambda d. Okay. And corresponding to this lambda1, there will be one vector v1, right? Eigenvector. And this corresponding to lambda2, there will be second vector. So similarly, there will be having d vector, and this all will be like orthogonal. Okay. So they will be perpendicular to each other. Okay. Some j equals to 0, like dot product or the perpendicular to each other. Okay. So see, so this is the final result I'm telling you, that the final result that you'll get. So lambda1 is what? The lambda1 is the maximum eigenvalues corresponding to the covariance matrix or the feature matrix. Okay. So lambda1 is the maximum value. Okay. So whatever the vector you are getting corresponding to the lambda1 will be your this direction. Okay. So if you want to change from D to D dash, and where D dash is smaller than D, so what you need exactly? You need the D dash direction. D dash direction that will be, you will be getting from that eigenvalues, the eigenvector itself. Okay. So when you will construct when you are having the covariance matrix S, and you will see that how generally you get, like if you go to the lecture also. So sir has proven like how will you get in the end, you'll be getting all the vectors like v1 vector that we were starting in the, from the starting we were telling this direction. This direction is nothing but that eigen vector corresponding to the maximum eigen value. Okay. Is it clear?
Yeah. One question: the eigenvalues you had written out there as lambda 1, lambda 2, is it in increasing order, decreasing order? Please, once again.
It's a decreasing order, like the,
Decreasing order. Okay.
yeah. So the vector v1 will be corresponding to the maximum eigenvalues, and this eigenvector will give you the direction where the variance is maximum. Okay. So if you need two dimensions, so you will be taking care of only two direction of the eigen, like v1 and v2.
Okay.
And v1 will be corresponding to the maximum eigenvalue, and this is, v2 will be corresponding to the second largest eigenvalue. Okay.
Okay. Okay.
So this was the final solution. Okay, but I'll start from beginning again. So this is a like final result. This should be there in your mind. How generally, what is that direction, and how generally we get that? We'll start seeing that. Yeah. So okay. So this is, yeah. So projection value, we got this one, right? This is a projection that we got, and this you can write in this form also, because U transpose xi, right? Okay. So xi this one, and what, so our problem is what? Our problem is our problem, or our optimization statement, you can say optimization statement, optimization problem, or you can say the objective of our work is, objective of this PCA is what? We need the variance of this one, whatever we got, U1 transpose xi 1 plus n. So we have to maximize this, right? We need to maximize this, and while maximizing, I need to get the UI. Like if I have to convert that to one dimension, 1 second, I'll just close my door. Okay. So what is our problem? Like this is our optimization problem. We need to find UI or U1 if I need to convert that to one dimension. So I'll be needing UI if I have to convert that to a ith dimension. So I need UI, and while finding that UI, I need to maximize the variance, right? So while maximizing our variance, I need to find UI. This is our optimization problem that I need to solve, correct?
Yeah.
Right? So from the starting, we are doing the same thing. We are just maximum. We just want our direction where the variance is maximum. Okay. So this is our problem. So I just wrote in the like mathematical form. So I need to find UI where I have to maximize the variance. That's it. So what is the formula for the variance? This one, right? UI transpose xi minus, I need to take variance is simply the distance from your mean value. Okay.
Yeah.
And mostly the mean is zero itself, right? Mean is zero. Why mean is zero? Because if we are getting some data set in the starting itself, while doing the feature engineering, we generally standardize the data. Like for each of the columns, we make generally we do, there is a one, what you can say, feature in the sklearn. We use that as scalar normal. We generally put for every column, we generally standardize the value. That means we are just putting the variance to be 1 and the mean to be 0. Okay, for each of the columns generally we do in the starting itself. So whenever you'll maybe most of you would be knowing about that, how generally we do the feature engineering in the, like if I'm having the data set. So in the starting itself, we generally put the mean as a 0. In the stats 2 also you'd update. So generally we do this as a 0. So S bar, or what you can say, the mean value for each of the column is 0. So this is and the constant is what? Constant means the condition. Okay. So for while solving this problem, what is our condition? So what is the condition that we are putting? So we are just putting only one condition, right? So this vector, we are just needing this direction. The direction, this, so unit vector I need, right? Because we are not caring about the magnitude. So I need just a unit vector. So for the unit vector, what? So ui u transpose should be equals to 1, right? This is the only condition that I'm putting for ui. And this is our problem. This is our optimization problem. So I need to get ui while solving the variance, while maximizing the variance. That's it, right? So this is the one way to solve. And this method is generally solved with there are methods to solve the optimization problem. And the one of the best method or one of the good method you can say is the gradient descent that generally we read to solve this type of problem. Okay, and this method. So this is the one method. Okay, can somebody like tell me if I need to solve this problem without using the technique of variance, maximizing variance? What should I use now? So I'm not knowing about the variance. I need this direction. Okay, I need this direction. So what should I do? Like I don't want to go in deep regarding the variance. I just want some other method to do this. Like you would have read in the first week also regarding something you would have read to get the direction that is like what do you can say, the
Regression.
regression, like what in regression?
Minimize the error.
Yeah, solid. Yeah, this is what we generally do. So if I need to either maximize the variance while solving your optimization problem. So optimization problem is simply a math that like I need to find a x. Here I need to find u. Okay, I am putting some condition on, like in the childhood we used to solve like x or something we used to solve in class 10 and all. Okay, and there were some condition on x. Here also we are doing the same thing, but it's like a bit complex one. So we need to get some help of some algorithm to solve this problem. Okay, so here also I'm solving the x. X means here view. So I need direction, some direction. I just kept some constant or some condition on that direction. See, that direction should be like a unit vector. That's it. So that constant also I'm putting. I'm putting. The problem also I know. I need some algorithm to solve that problem. That can be solved with the help of Lagrange method also. But that we'll see later, or maybe in the lecture sir has discussed that. Okay. So and the second method is you can reduce the error. Okay, by reducing the error also you can do. Okay, so I'm having this is the one vector xi, and this is the projection, right? So the projection is this one, right? This is the projection. So what is the reconstruction error? This is the reconstruction error, di. Fine.
Yep.
Correct.
Yeah.
So we can do that in that way also. Reconstruction error, minimizing the reconstruction error. Either you are minimizing the reconstruction error or maximizing the variance. Okay, from the both the mathematical statement you'll end in the same final conclusion, the same direction you'll be getting. Okay, so we can do the di square I to n, I equals to 1 to n. What I need to do here, I need to minimize this. While minimizing this, I need to find ui. Correct. So I need to find the direction. Okay, and I need to minimize the distance. I need to minimize the reconstruction error or the distance from this point, like from the exact point and the projected point, whatever we have projected on that data set. Okay, so di can be written as what? So di can be hypotenuse like xi square minus this one. This I can write like this. So here also our objective is this one. This is objective function only, and this di square can be written like this, summation of this one and this. Xi square minus what is the projected value? The projected value by ui transpose xi whole square. Right. So this is what we are doing. So here, so our optimization problem becomes summation of all this point. So the distance, or you can say this one, xi whole square minus ui transpose xi whole square, right? So this is the distance that we generally get, and this is I1 to n, and this I need to minimize. This distance I need to minimize, and this is what reconstruction error. Reconstruction error. Okay. This I need to minimize, and while minimizing this, I need to find this one direction, this ui. Fine. And what is the constant here? So I need to find the x, and what is the condition on that x? So what is the condition on this ui? So the condition is what? This is a unit vector. That's the only condition that I need to keep. So ui transpose u equals to 1. This is a constant for our optimization problem, and this is the optimization problem or the objective. So this is what I need to solve. That's it. Okay. I need to, and then I need to find the u. Is this clear till now? Right?
Yeah.
Okay.
Yeah,
Anybody is having any problem?
Sir, is maximizing likelihood related to this somehow?
Yeah.
Okay, so like it's
Maximum likelihood, like it can be used like when you are maximizing the variance. Okay, there can be like there can be a lot of method to solve this problem. I'm just telling you how to like, what is the problem here. So a problem is the what is the optimization problem. So you'll whenever you'll be going through some algorithm like PCA. So the math behind this is what we are just concluding to some objective or what I need to solve. So this is what I'll be giving to the PC or the SQLN to solve my this problem. This can be solved with the maths also with but this problem I'll be giving to the computer. Okay, to solve my problem, and I need to get U1. I just gave all the things, like I just gave all the information, and that need to solve my problem, and that can be solved with your like whatever you told maximum likelihood method also. That can be solvable with the Lagrange method also. Okay, but Lagrange multiplier method also that can be solved. Okay.
okay. Okay, thank you, sir.
Yeah. So there are like n number of methods that like to solve a maths problem. You generally have a lot of like you can use as many like conceptual like concept to solve any problem, right? So it depends on the like people's also like how generally you which concept generally you use to solve this problem. I guess Saul used the Lagrange multiplier to solve this problem in the exam in the lecture. Okay, so can somebody tell me why generally use this unit vector only? Why can't we use some other? Why generally want a unit vector only in that direction?
easier to compute.
Easier to compute, yeah, it's fine. But like I'm maximizing this variance. If I'll take u as a infinite, it will maximize, right? That also. If I am having this function ui transpose xi, if I'll take u if I'm not taking this as a unit vector, I'm just taking u as some infinity.
Mm-hmm.
I need to maximize this function only. If
Yeah.
I'll just put infinity here,
Yeah.
right?
Yeah.
So that's why generally we put a constant on that condition. That should not be like
Okay.
it should be a unit vector. Okay. So
Okay.
this is what generally we take the constant here. Okay. So only two method has been discussed in the lecture also. The first method is to maximize the variance, or you are minimizing the reconstruction error. This is the only the two, like there are some other methods also to come to just the optimization problem. But with the help of these two methods only, we can solve this. With the help of these two like concepts, either you are maximizing the variance or to minimizing the reconstruction error. This is sufficient to conclude to the optimization problem and the constraint. Okay. Okay. So yeah, so the solution part I already told you what is the exact solution in the end, but I'll just go through that. I'll just delete this. But I have that I just wrote somewhere. I'll just check whether it's there. Okay, if you want to see this, okay, I have this link. Okay, so this is a blog that you can read also. So this is a blog for the MNIST dataset. So maybe this will help you to get a brief idea regarding the how does that PCA works. Okay, so here in this, why it's not working? Okay. So in this MNIST data set, MNIST data set is a simple data set that consists of like that there was a like whoever has done this, like somebody has just wrote with the handwritten word from 0 to 9, okay, and from that 0 to 9 words whatever has been written, so some person has what he did, he just why is not working, okay, so whatever we were having, like for example 0 is written or 4 is written in the handwritten form, so he has just converted that into a 28 cross 28 pixel. Okay, so 28 cross 28 pixel, and each of the pixel would be some value like 0 or 1. So like for example, you can see for this one. So for one written, like handwritten one, so this was the pixel value. So this was the pixel value. You can see this like 28 cross 28. So the pixel value was varying from some 0 to 1. Okay, so 28 cross 28 means how much? Like 784. And this all the each of the data set, each of the point, each of the pixel was taken as a one dimension. Okay, to convert that like. See. So what I was having some like 0 to 9 it was written. Okay, and each of the written word was converted to some 28 cross 28 pixel, and each of the pixel was having some value. Okay, and each of the values has taken as one dimension, so like 28 cross 28 is how much? So it's like 784. Okay, and this 784 has taken as the dimension like from d1 to d784. So one value is like for example this value for all the points, like for in this example I guess the writer has took I guess more than 60,000 data set, I think so he took. Okay, some random n values he took. So for some n values, for n handwritten words from 0 to 9, okay, for each of the steps, he just took the 28, he just converted that into a 28 cross 28 pixel, and for each of the values, he made like 784 dimension. How did it came? Like for example, for one example, I'm telling you, like it's written one here, handwritten one, and for this handwritten one, 28 cross 28 pixel values was there, and for each of the values, he took each of the values as one dimension or one feature. Like for example, if this is written as one, he took the first value, the first one cross one in the one cross one, whatever it was written, he just took this as a one feature of that data set. Similarly, if this was written two, and here it was written something in the first box, he took this as a in the D1 itself, the D1 value for the second data set. Okay. Similarly, from here to this end point, he took each of the pixel value and converted that into a feature matrix, and each of the feature of that matrix was related to the pixel value. Did you get the point? How did he did that?
When you say the value, is it going to be treated as 0 or 1, or how is that? Because one
Yeah.
pixel, okay, that's fine. Direction, like when you write 1, it is going, all the pixels are going in one direction. So how do we interpret that?
Okay. So see, I'll just tell you again. Like here it is written one, right? So
Correct.
this okay. So this was having some pixel values, and this pixel values is written in some like the value has been normalized. He just used some basic engineering technique, feature engineering technique to convert, like if this is a like if this was like this, so if this was written in the handwritten form, so
Hmm.
there will be some pixel value. So here all the here will be zero, right? Okay, and
Yes.
depending on the, maybe he would have converted the normalized value depending upon the mark, like the blackness of the mark, right?
Hmm.
Right here.
Hmm.
For example, here it was written the pixel. Okay, so here you can see all the other values. The values were zero. Whenever it was written here, so it depends on if there is a very dark like one here, like you can see the dark black. So the
Yep.
value was like almost 1 1 1 1, right?
Yep.
And whenever there is a darkness has become like brown or something, the values has reduced 0. 0.8, 0.
Right.
0.6, 0. 0.7, right?
Right.
So this is how he would have like he just used some like random stuff to give the values to the pixel. Okay, and this random stuff, whatever he has used the concept to give the values, the normalized value, he just gave to all the data set whatever he was having.
Uh,
Okay,
okay.
so yeah, so this he did for all the data sets. So he was having some 60K of written, handwritten wording, like from 0 to 9. For all those 60K data sets, he just converted those to some pixel values. And from each of the pixel values, from starting from here, like this 1 cross 1, this is the first element of this matrix 20x cross 28. He took this as a D1, like the first element of the first feature. Okay. Similarly, this he took as a second feature. He took the third feature. Similarly, he took this as a in point as a 784th feature of the first element or the first data point. Okay. Similarly, for each of the other data point, like for example, here it is 2. For 2, there would be some pixel values, right? So similarly, he took for all the, like for the first, he took from here to here all the different features, all the element of this pixel value he took as a separate data point, not data point, separate feature. Okay, is this clear?
Yes, sir.
Um,
Okay, I'll just maybe. So I'm having, like for example, this is not 28 cross 28. Like for example, see this, he has just converted all this point as a 2 cross 2. Okay. And for 2 cross 2, he has just converted. For example, I just telling, in spite of 780 28 cross 28, he just converted that into a 2 cross 2 data, 2 cross 2 pixel values. And in that 2 cross 2, this element, okay, so whatever the element was here, he just took as a D1. D1 means the dimension 1, D2, D3, and D4. Like D1 is the feature 1, D2 is the feature 2, D3 is the feature 3, D4 is the feature 4. Okay. And for each of the every point, like I'm having like 60K data set. So 60K handwritten word are there. So I've just started from the first. So for the first, there would be some 4 values, right?
mhm.
Similarly for 2, there would be some 4 values.
Yeah.
Yeah. So here, what he did for 28 cross 28, he took each of the data point as one feature. So here, if I'm able to convert that into a 2 cross 2, I'll be having how many features? 4 features, right? So here he was having 28 cross 28 features. That is 784 features. So he did converted that all the data set into a 784 features, right? Till now it's clear, right?
Maybe if you proceed further, we'll ask.
Okay. Okay.
Maybe,
So
sir, if we can, sorry to interrupt, maybe if we can take one numerical example or something at the end, so we can kind of.
okay. Okay. So Hmm. So what he did, he just took all the written words and tried to convert to some pixel values, and each of the pixel values he took as a one feature for all the points. And in the end, what he did, he was having all the this 0, 9, and 2. He was having a lot of data sets. And in the end, what he did, so this is the PCA. So see, you can see this. So I was just in the starting. I told you in the PCA we do the PCA for two aspects. One for the visualization perspective and one for the reducing the dimension for the model training. So here the MNIST dataset, this generally is famous as a MNIST dataset. In the MNIST dataset, the publisher who has published this blog has just tried to visualize that, because in the handwritten from 0 to 9, okay, that was after converting that to pixel values, he was having 784 features. Okay, so 784 features can't be seen, can't be visualized, right? Because we can't visualize those 784 features. So what he did with the help of PCA, he just tried to convert that 784 features to a two-dimension features, two dimension. So he reduced 784 to two dimensions. So he converted from 784 to two dimension. And after that converting that dimension, so he just published in the paper, he was able to view, like, see, you can see this he has converted from 784 to two dimension itself. Okay, and you can see these are the data points that is representing one. So this is the help of PCA only. He used some 2-3 lines of code and tried to convert that from 784 to two dimension, and with the help of PCA only. So you can see this, all these data points represents one similar type of. So you can see if else statement can also be applied here. So you can see this 1 1 1. All the data points represents one. Okay. So much of the information is preserved also. Like not all, but like almost like he is able to preserve the informations also. You can see this, right? And if you go here, this represents 0. Okay. But if you go here, then it's like maybe the feature that there are so many limitations also. I'll tell you what are the limitations. So this here, like, this has not been like, it's not like pretty good. But yeah, for 0 and he for 1 and 0, he was like, he just bifurcated nicely, fine, from like 784 dimension to 2 dimension, and he was able to visualize also. Correct.
Uh, which one is the visualization? The one in the center, or the where you are showing the numbers?
See,
Yeah.
so in the starting, what he did, he just tried to convert the bigger dimension to a smaller dimension, very small dimension, only 2 dimension. And
Right.
if you see this, these are the data points. After visualizing, he got this as a data point, and he just shown this is the points where it represents 1. After converting from a very bigger
Okay, so
dimension to 2
wherever you're
dimension,
pointing the mouse, that is the 2 dimensions on which it is the
yeah,
x and
yeah,
y
yeah,
axis
it has been
numbers. Okay,
converted to a 2
okay.
dimension. Yeah. And you can see the
Okay.
values
Now I
also,
understand.
one its own, right? And here, if you'll move here, you will show the different number.
Yeah.
Right? And for this values, it has, so he has just used the PCA only to convert from a bigger dimension to very small. There are some other method also he has used, like, so this is the other method. I don't know which method I didn't try. But yeah, this is the PCA that he has used. So this you can like, maybe other MNIST is very famous data set. Generally, the people, even when I was reading, I just went through this data set.
Would you be able to post this link on the chat? Would
Yeah, I'll just
be
post
nice.
it.
Yeah.
Yeah,
Thank
I
you.
just posted. Okay. So I'll just go. So this we have already discussed regarding this is the problem that we need to solve. So this is the alternate method that I told you. So the first method was the maximizing the variance, or the second method is to minimize the reconstruction error. And this is a solution to our optimization problem. Okay. So this is so yeah. So I'll be directly going to the result. How did we get that? Maybe you can refer the lectures that I like. Is one lecture sir has went through the proof, but maybe it will give you a lot of pain, because in like the method is like really complex. With the PC you can do it like in a, just you need to write 3 line of code. But yeah, in the mathematics, you have, if you'll go through the lectures, will be, if you are able to get, that's well and good. Otherwise, maybe in the Saturday session, along with the solve with us, Ram will discuss those points. Okay. If you have any problem, otherwise I'll discuss you the solution, like the problem I told you, what are the problem that we are solving in this PCA, and we'll be getting to the solution, what is the exact solution for that problem. So the exact solution I told you also, this is the data, like the data point I was having. So this is our 1 to D. So this is the features I'm having a feature matrix. This is the feature matrix. This is X transpose, Xi transpose. This is the D feature D. So I'm having the matrix which consists of D dimension and n element or the n data set. So you can compare this with the MNIST data set. In the MNIST data set, how many we were having the D as 784, right? And I was having X as what, 60K. And I just converted from 784 to 2 dimensions here. I just converted to 2 dimensions, right? So in the solution, the exact solution, this you should be aware, or you can say that you can remember also. This is a final conclusion that we generally get. So before we are getting, so this is this is not of your use. This pre-processing and all is like when you will be going through ML techniques, you'll be doing that. Okay. So the covariance matrix, you should be aware of that. That a covariance is what X transpose X. X is what feature matrix that you are having. So feature matrix is what, if I'm having 780 for that example, so I was having this pixel value for each and every case. Or this is the other example also you can like see, you already have been given some data set. Okay, that data set consists of n element, and that each of the element was having d features. That's it. So you will be having n cross d as the feature element, feature matrix. Okay, and if you are having that n cross d feature element, feature matrix will be coming to a symmetric, square symmetric matrix, because you already know that X transpose X will be some symmetric X square symmetric matrices. And as the X is the feature matrix and consists of n cross d, so you'll be having X transpose as d cross n. So you'll be ending with d cross d element covariance matrix, and d cross d will be having, I told you, eigenvalues. It will be having a d eigenvalues, and those d eigenvalues will be having some magnitude. And if you see the magnitude of the eigenvalues, so some of them will be a bigger and some of them will be a smaller. If you right, so d eigenvalues will be there because I have a matrix of d cross d, and corresponding to each of the eigenvalues, I'll be having d eigenvectors also. Okay, right? So eigenvalues, I am having an eigenvalue. So this can be written in the form of increasing or decreasing order. This is written in the form of decreasing order. So lambda one is the eigenvalue that has the maximum magnitude, and corresponding to that lambda one, I'll be having some vector also. Okay. So okay, this is fine. This I told you, like all the vectors will be perpendicular. This everybody knows also. Okay. So what I was trying to say, so whatever the vector you'll get, so if we are getting v1 vector, so v1, so we were, so from the starting we used to find that solution, and we were finding the solution for that one direction. Okay, that one direction that should be having maximum variance or minimum reconstruction error. And what is that direction? That direction is the eigenvector that is corresponding to the maximum eigenvalues. Okay, so if I need to convert that some n dimension, some d dimension, for example, I'm having some 10 dimension, I'll just write it. Like for example, some d dimension, 10 dimension I'm having, d 10 dimension means I'm having 10 features. Okay, and I need to convert that 10 features to some 2 features. Okay, so while solving the optimization problem, I'll be reaching to that conclusion that these 2 features will be 2 features is was 2 direction, v1 and v2, and v1 is corresponding to the maximum eigenvalue, and v2 is corresponding to the second maximum eigenvalue. Okay, so this is how generally we do. Okay, so this is the steps that generally we follow. This is a column standardization that we do before even feature, that we generally, if you're having the matrices of the, what you can say, the data set, this generally we do to make this x bar, the mean value as 0, and the variance of this column as 1. This is a step that we follow. If somebody wants to do the PCA whole with this is a 4 step that you need to write the codes and you'll be able to do. And then in the PCA algorithm also, this 4 step is only done.
In the 4th step, what is the first thing? N1 is equal to V1, or what is that
Where?
means? In the 4th step,
Oh, this is U1. This is the
U1.
direction that we
Okay,
were
U1.
finding, right?
Okay.
This U1 is corresponding to the V1, the
V1.
eigenvector
Okay.
first.
Okay.
Okay. Uh, so this is like all the steps are like, see here, if you will see that. So you generally got the U1 as V1 only. V1 is the eigenvector itself. So for example, this is a simple data set I'm having. If d is equals to 2, if you are able, if you want to convert that this 2d, so in the starting we want to convert that 2d into a 1d. So what generally you will do, so you'll be just finding this vector, right? So the v1 vector you need, right?
Yeah. Yeah.
So if you want to convert it to 2D to 1D, you will be just caring about the V1 vector. You should not care about the V2 vector, right? Because in the V2, the variance would be minimum, right?
Yeah. Yeah.
Hmm. So so if can somebody tell me? Okay, so if, for this data set, for this data set, tell me from this both the example which one is correct. For this data set, lambda 1 is 3 and lambda 2 is 2, and lambda 1 is 3 and lambda 2 is like 0. Which is correct? Because see, why I'm asking
Second one
this,
will be
because
correct.
which one?
Second one.
Yeah, second one is correct because
It's a
the
clear
second
distinction.
direction is not giving any information, right?
Yeah. It's a clear distinction. 0. Yeah.
Yeah. So this should not be exact 0, but like almost
Very
around 0
small.
only.
Yeah. Yeah.
Yeah, because the data set I was having a very fine data set. Okay, so this
Yeah.
will just give me the direction because the spreadness is very less in this direction. So it will like that the other direction is not like important at all, and then you will be yeah. So this is what generally we. If you are having like for example this type of data set, okay, I just wrote it in the okay here I just wrote it. So yeah, this is what I do. If you have like d and 10 dimension or 10 features, so this is the 10 lambda value you'll be getting, and 10 eigen directions also. And the first eigen direction that is corresponding to the first eigen value that will be having a maximum variance, and the last will be having the least variance. Okay. And one more thing. Okay. So if like for example, this is our data set. This is I'm having feature 2 dimension F1 and F2, and this is our data set. Okay. So this is our data set. So the direction that I'll get is V1 and V2, right? So V1 is the important one, and the V2 is not important if I need to convert that 2D to 1D. Okay. So so I need to get the information also. Okay, how much information I have preserved. Okay, so how much you have preserved? Like for example, if you have converted this 2D to 1D, okay, because you have just you have just removed the other feature, okay, other dimension you have just skipped, so that was corresponding to the lambda equals to 0. So here, so the information that is preserved, there is a formula for that lambda, the corresponding lambda that you have kept upon the summation of all the lambdas. Okay, so for this example, for the first example, I just skipped the one direction. That direction was corresponding to the eigenvalues 3, and I just skipped the 0. Okay. So for this example, I can see that the information was preserved at 100%. It's not 100%, but it's almost like all the information I have preserved by just removing the V2. Okay. I just kept the V1, I just skipped the V2, and then also I just preserved 100% of the information. You can see that, right?
Yes, sir.
Mm-hmm. Mm-hmm.
Yeah. So similarly for this example, you can see this is a data set. This is the other data set. And for this data set, I'm having lambda 1 as 3 and lambda 2 as 1. So how much of the information we are able to preserve by how much information I'm like able to preserve means I'm just from 2D to 1D when I'm converting, I'm able to conserve only lambda 1. I'm only conserving the direction corresponding to the eigenvector eigenvector corresponding to the eigenvalues where the value was 3 or the maximum value was there. Okay, I'm just skipping the eigenvector that corresponding to the lambda value 1. Okay, so I'm how much information I'm able to preserve. This is lambda 1 upon lambda plus lambda 1 plus lambda 2. So that is around 75% of the information we are able to preserve for this. It's not that good, but yeah, it's fine. Okay. So similarly, if I'm having this type of ellipse where the lambda 1 is 3 and lambda 2 is 2, and for this, if you have been asked to convert that from 2D to 1D, so you are able to preserve how much information? 60% of the information. This is like really not that good, right? Okay. And if you have the data set like this is a circle type of data set for both the lambda 1 and lambda 2. So if you have been asked to convert this 2D to 1D, so you are able to preserve how much of the information? 50% of the information, right? 3 upon 3 plus 3. So you are able to preserve 50% of the information for this example, right?
Mm.
Yeah. Like
One
other,
small question. What
yeah.
does lambda 1 by lambda 1 plus lambda 2 actually represent, or where does it come from?
So
It's
this
a contribution, is it?
yeah, this is the contribution, like how much of the information you are able to preserve after, just like for example, you just converted 10 dimension to 2 dimension you preserve, like, right? So so you'll be having some 10 eigenvalues, right?
Mhm.
So you just kept 2 eigenvectors, like corresponding to lambda 1 and lambda 2. That was maximum, right? Lambda 1 was the maximum and the lambda 2 was the second maximum, right?
Mhm.
So how much of the information you have preserved? Or you can, whenever you are solving some, like, you're applying some algorithm, you'll be trying to get some, like you want to convert that 10 dimension to 2 dimension, but you also want to preserve some 80% of the information. So how will you do that? So you want to convert, like for example, I'm telling you, you want to convert from 10D to some not 2D. You want to convert some 10D to ND, some D dash, and D dash
Mhm.
should be less than 10. Okay, and you want to preserve the information like 80% of the information. Okay, so what you'll ask the algorithm, you'll ask you, okay, the summation of the lambda, okay, lambda 1 plus some n lambda d dash upon all the lambda should be greater than equals to 0.8. Like you want to preserve 80% of the information, but you also want to reduce the dimension. Okay,
Mhm.
did you get the point?
Ravi,
Okay.
can I say something here?
Sure, please.
This is based on my understanding. So what we are trying to do is, of because we are reducing the entire data to certain features now, which gives us and helps us to preserve most of the information of the entire data set.
Mhm.
Of say here in this example of 10 dimension 10 features, we are taking those many features which will help us to preserve 80%. So this is nothing but the ratio of the features that we maintain as against the total features in the data
That are
set.
there. Okay, the
Yeah.
significant ones.
Yes,
Okay, okay,
that's what we are doing.
okay. Thank
So
you.
am I correct?
Yeah, it's totally correct.
Yeah, okay. And so what do we do in cases where you showed the last example where it's a circle and only we can preserve 50%? So what happens to scenarios like this?
Yeah, so this is the limitation. So I was just talking about the limitations. I'll talk about the limitations also.
Okay.
So yeah, so these are some of the limit. There are so many limitations that I know for the limitation of the, so where you should not be using, okay, the PCA. Like, people generally use, but okay, these are the some of the limitations. So the first limitation is this one only. If you are having the data set as like this, okay, so for this data set, you can't do much, because if you are doing, you are like almost like you are losing 50% of the information, right? That I have converted, like I calculated also. Okay, like here, if I'm having two features F1 and F2, for if this data set is in the form of circle, you can expect this lambda one as uh, some some constant value 3 or 4, anything, or lambda 2 will also be same, right? Because it's a circle. So the information that you are able to preserve, if you want to convert that 2D to 1D, so the information preserved is how much? Lambda 1 upon lambda, all the summation of all the lambdas. So that is lambda 1 plus lambda 2. Okay, so 3 upon 6. So that is 0.5. So you are able to preserve only 50% of the information. That is really bad. It's not at all good. Okay, so for this type of problem, so this type of problem, the PCA won't help you much. Did you get the point?
Yes, sir.
Yeah. So similarly, there are other limitations also. Is this clear to everyone? Like this limitation, the first limitation of
Yeah,
the
so
PCA.
how do we, I mean, like we should study the data first and only then go for the method, is it? Is that the way would be a good approach? Because,
See, I'll tell you one example. So in the MNIST dataset itself, MNIST,
Mhm.
if you have seen the MNIST dataset, I
Yeah.
told you it will work like when generally people doesn't see much about the dataset. Generally, he does. Like here also, what he did, he just tried. He for the MNIST dataset, he just tried to do, like he was having 784 dataset. Okay, so he didn't care about the how the dataset was seen in the 784 dimension, because you can't see that.
Mhm.
Here we were having two dimensions, so I told you, okay, this is in the form of circle, so you can visualize the scatter plot and directly you can say, okay, so this is the first limitation of the PCA, because
Correct.
you were right. But if this is in the form of like 100 of dimension, you can't see that data
Definitely
set
not.
itself,
Yeah.
right? So like here he was not able to see that dimension of 784. Okay, so what he did, you can see that for 0 and 1, he was able to he was able to like separate that 0 and 1, okay, easily. But for this data point, you can see this is not separable. Like here, you can easily use if and else condition, some v1 value, some constant value, right? But for this value, like it's a messed up. Okay, here we are not able to visualize clearly. Yeah, that's why in the last, the PCA is like a very old technique. Like here now also we are using, but there are very like nice algorithm also that has came, that we are using also.
Okay.
And so what happened in this example? I'm telling you this. See what happened here. Like I'm just trying to give you the example. F1 and this F2. See, for this MNIST data set, I think so what would have happened if I'm having this data set, and if I have the cluster like this, if I have here cluster and here clustering, and here also the clustering as there the data set, the clustering of the data set. So what would have happened in the MNIST data set? So if I'm having this, so if you'll see, so the two line, two, what you can say, that two important lines would be with this one, right? This one and this one. These are the two the dimension that after converting that PCA to a two dimension that I'm needing, right? To F2 and F1, right? So this is the cluster of one data set. Okay, this is a cluster of other data set, right?
Yeah.
This is the cluster of second, the third one, and this is the clustering. Okay, if I want if I want the direction where the variance is maximum, so here the variance is this much, here the variance is this much, right? Here the variance is this much. Okay, so if somebody wants to, if somebody wants the direction where the variance is maximum, so what the PCA will give you? The PCA will give you this direction only, right? This and this direction, correct? And when you will calculate the variance, okay, for this data point, that is fine. It will project all the data point here. For this data point also, it will project here. But for this data point, if it's projecting on this, like if you are like what it did in MNIST data set, what it did, yeah, MNIST data set, it converted from 784 to 2 dimension. Here, I want to just convert from 2 dimension to 1 dimension in this line itself. So it will project all the data set here, right? And similarly, it will project all the data set of this point also here. So here it will get messed up, right? So for this data point, it will not be able to see which point will represent what. Did you get the point?
Yeah.
Yes, sir. Now we know, because I was getting confused when you said these points are, clearly visible or segregated from the clusters that is there.
Mm-hmm. So that's why
Yeah.
I think so. This MNIST data set was not able to like separate all those data points because it got messed up when. So if here we are just, it's a simple example. We are just converting from 2D to 1D. There it has just converted from 784 to 2 dimensions. So you can see how much like complexity would have happened there, right? So here also, this is also the second limitation. This is also the second limitation of the PCA. So if you want to convert that, and if this data set got messed up, so it will be very difficult for them to work.
Yeah.
And sometimes there's the third limitation also. So sometimes what happens now, if you are having some data set, like for example, this is a data, and your data set is like this, your data set is like this, like all the data set is on this structure. And if you want to convert this from bigger dimension to lesser dimension, what you lose the shape, like you lose the structure. And if you're losing the structure, it will not, like the PCA won't work properly. So this is also, I think so. This as of what I know, I think so. These are the three limitation of the PCA. There will be like a large number of like. That's why we are not using much. Like yeah, but one guy was saying like we are using now also in the industry. That I'm not like it will be used like many of the basic algorithms that we use, that I'm pretty sure. But this for the PCA, there are some other algorithms also that we generally use nowadays.
So are we going to cover some other algorithms also which can take care of these limitations?
Here, I think so. In the next, I guess, if you would have taken ML techniques, I guess ML techniques will be having will be going through a large number of algorithms. In the MLF only, we'll be just going to the PCA. What is the because here we'll be discussing what is the optimization problem, what is the objective, okay, what is the solution for that. From the next week, we'll see how generally we solve the optimization problem. So whatever the optimization we were having, we'll see how generally we solve the optimization problem. If that is constant, if that is not constant. So from the next week, we'll be seeing how to solve the problem for like 2 3 weeks, and that is it for the machine learning foundation. And now from I guess from the ML techniques,
Okay,
you'll be
sir.
reading all the algorithms and all. So this was a basic ML. This foundation is like very basic. Only you'll be reading some vector, linear algebra, so all the various basic aspects that we'll be using in the other algorithm, that when we'll develop some algorithm, we'll be using some this all basic math. You'll be using these concepts to develop the algorithm.
Okay.
Okay.
So in this foundation, you'll not be going through any of the algorithm. One algorithm you'll be going through. In the clustering, you'll be going through one algorithm, and that's it, I guess. Yeah, that's it. So you'll not be going through much of the like algorithm in this foundation course. But yeah, for this PCA you can work. Like if you are good at coding, you can try. I'll just give you so many data sets are there in the Kaggle. You can find so many data sets, and you can just try to convert that from a bigger to a smaller data set. Maybe with some Python code, and then you can use the sklearn library to do the sklearn library. Like it's a very one line of code, okay, to convert that PCA. But yeah, with the Python you can try to get the covariance matrix, calculate the covariance matrix for the feature. Just do some feature engineering for that matrix feature matrix, and then try to calculate the covariance matrix, then the eigenvalues, eigenvector, and then try to reduce that. Maybe that will give you a better clarity.
So can we have any some toy problem with some numerical numbers to actually calculate,
Okay,
practically see
calculate.
how? Yeah.
Okay, now I think so. I don't have
So is this sheet available anywhere? The
this.
one which is scrolling right now, the one which is
Which one?
scrolling right now, the document,
The
the
document.
PDF.
So this one.
Yeah.
Okay,
This one and the other one also, which you went. So the other one which you were explaining.
this one.
No, no, sir. The PDF that you were using.
Okay, that today itself I wrote. Okay, I'll just upload that somewhere. Uh, like in the same
Yes,
PDF,
sir.
like same
This.
file I'll upload there.
So, but where are all these files saved or
Uh,
uploaded? Is there any drive or
yeah, I just uploaded
But
on the OneDrive. I just
so? How
shared
do
it
we access
on.
it? Because I do not have access to any drive. Whenever I try to access, it says access restricted.
Okay, I'll just paste the link now itself here. But I think so. I just posted on the Discord also. This link. This is the revision slide. I guess I shared 2 3 times.
So
I
what
just
problem
upload.
is?
I generally upload everything here itself. Okay, so you can just
Yeah.
go through that. It's like I'll just paste it now. Most of the notes are there. Like most of the notes like that I made. Like that most of the things will be like in the handwritten form.
Okay, sir.
The other aspect, like because in the portal mostly we upload in the form of latex or many like, but here I guess all the stuff like the solution also will be there in the form handwritten. All the detailed solution will be there in the handwritten form.
Yes, sir. Got it. Thank you.
So I'll just upload that file also. Where is that?
So honestly, I understood PCA today after so many weeks.
So but the PCA week I guess started today. It's like this Friday itself, right?
Yeah, no, but we had this in the first week of MLT.
Oh,
But
MLT. Okay, you took that MLT. MLT, yeah,
yeah,
PCA is in the first week itself.
and so the best part is there was mention of eigenvalues and all this terminologies which were not introduced to us. So for us to understand MLT itself was a bigger challenge because we did not know these words what they meant.
Okay.
Because eigenvalues, we only did it in the later weeks of MLF.
Mm-hmm. Okay. Okay.
So why is the course structured like this? It's all jumbled up.
This time
Not
it
really.
happened.
No, not really. Because if you had taken MLF and followed it by MLT, it would have been a lot
Yeah.
easier for you.
That is
Yeah.
true, but when we selected the course, it says it's a co-requisite and not the prerequisite. Had it
No.
Mm-hmm.
been pre, then
Yeah. Okay. Got it. Got it. Sorry. Continue. Sorry to interrupt, but continue. Yeah.
that's why I know, Ravi, what you said, but
Now, what I mean to say
just
is
for
this course recommendation that is coming, right? I know what you tried to do because I also tried the same thing. Then I looked at what are the recommended courses. Recommended courses were MLF and BDM. So I just picked them. That's all.
yeah, that's true. But MLT isn't that, there are certain weeks which are good enough, like clustering and all.
Mm.
That didn't have any dependency on any other
Correct.
concept. So, but
Yeah.
even
What
if
I
it is mentioned as core requisite, in that case also it should have been, some kind of a
The
what
problem happened like whenever we have a meeting, like many of like students generally tells, yeah, you should put like MLS, MLT, like I'm able to take those courses and also this time only it has happened like MLT and MLF you can take. Otherwise, last time it was not. Like last time you have to first do MLF, then only you can go to MLT, MLT and P you can take. But this time they've allowed for them like you can go for MLS, MLT at one go also. And many of the people I know is like struggling. I like many of them has messaged also. But like now you can't like you have to put what but the faculty is like awesome. I did some courses in IIT Madras in under Arun Rajkumar. Like he's like one of the best faculty I've ever seen.
no, so I mean, nothing to say about faculty is good, but the concepts need to be clear. Like, if somebody will wake me up from sleep tomorrow and ask me about PCA, I may be able to explain the concept. Though I need to work some more on it to, kind of uh,
Okay.
really understand it well. But whatever I understood today, I did not understand it for the past few weeks. So you can imagine the struggle that we go through.
Yeah, the PCA is in first week, I know.
Yeah. It was all, completely going above the head. Couldn't make any head or tail out of it.
Okay. So you can read like from the skill and website itself. Like there are so many, I guess. Yeah, but those generally give you a picture about the coding stuff from the skill and. So ML technique also has all the algorithm has been talked, right? ML technique I
Yeah.
just went through 2 3 weeks. I didn't went through all the content.
Yes, few algorithms based on, how to look at the data, and if they are in different structure, then how do we use them? Supervised and unsupervised learning under those two head.
Okay. Okay, and then you'll be reading the how to solve the optimization from next week.
Yes.
You already, I guess, it's already been covered in ML techniques, right? The
Yes, sir, but
second
we did
one.
not understand anything. So now is when, we are trying to, I mean, not we, I must say I, uh,
No, I would
Okay.
disagree on that one also. In the exam center, there are some who were saying the same thing. They did MLF and MLT. They're doing MLF and MLT together, and they are really saying it's going over their head. So you're not alone on that.
thank you, Ravi, for supporting.
You're not
I,
alone on
I
that.
thought I was the only one drowning.
No, 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 no. You're not the only one on that. And the other lady I spoke to, she also made the same mistake. She did not go with the recommended courses. I won't say
Yeah.
mistake. I think it was intentional. She was intending to do both the courses together, so she went ahead and picked. And
For me, this term was little lighter in terms of my other commitments, so I thought I'll be able to give some time. But given the time, the lectures aren't sufficient at all, because the problem is the concepts or the terminologies that are used, we are not aware of what they mean. So
right,
that's why there's double work going through those terminologies, trying to understand, and then trying to understand, the concept taught for that week.
correct,
So
correct.
that's where the struggle is.
Even I am actually having trouble with MLF because the videos are very, very much grounded in theory, and understanding the theory and then trying to see what the question I am trying to answer in the graded assignment is going to be.
Yeah.
Yeah.
And what if they can have any examples that can help, for me as a person, it becomes little difficult for me to comprehend from, the variables that they use, or the, if any of,
Definitely.
even one example is discussed that helps to understand the concept better.
True. True.
So can you give this feedback? At
What?
least some
When the
example
videos,
as part
when
of
the,
tutorial also can help.
yeah,
The
like
tutorial is there in MLF every week, like all sort of like problems we have
No,
discussing in the
sir,
video.
it
no,
is
no,
not
no. The video
sufficient.
is not having those kinds. Let me, if I, for example, if I had to put M2 and Math 2 and Stats 2, both professors, Professor Sarang Sane and Professor Andrew,
Thank
both
you.
of them solved some problems during the course. That actually gives a little bit of more grounding to the theory that is being covered. So that
Okay.
actually helped me understand it better. Sometimes I'm finding myself lost in the videos. After some 30, 40 minutes, whatever the duration of the video is, 30 minutes, why am I doing this is not really clear sometimes.
So from like I guess in MLF, first week, second week, like till
First, second,
fourth.
third were okay. First, second, third were okay.
Uh,
When it came into this particular aspect where we are talking about
Linear
we,
algebra
a
part.
linear algebra part. Linear algebra was nemesis even in mathematics too. So here, okay, linear regression, polynomial regression, okay, eigenvalues, okay. The moment it starts hitting SVD and everything, it's like, okay, now it is gone.
But sir, even in other cases, Ravi,
Yeah,
one small toy example can also help.
true, true, true. One problem, if it is solved there and shown
So
what exactly
that
it is.
helps us to put
Yeah,
things in perspective and see, what's the purpose behind it and what are we really doing. Because X transpose X, Y multiply by weightage, this, that. Sometimes we get lost, and towards like half of the lecture, or rather the entire lecture, trying to just understand what exactly is happening.
I like the way the professor is actually saying, you go and try this particular thing out of yourself and try this out by yourself, and here are the hints. That I like. But the precedence to that is missing altogether. So I don't know how to go and solve that and start, and then I'm stuck there for an hour and I'm like, okay, leave it now. आगे बढ़ बाद में देखते हैं, and then that
So
keeps
maybe